Imagine holding the master key to the universe. A single equation so elegant, so profound, that it could unlock every mystery from the smallest quantum particle to the largest galaxy. Einstein spent the final decades of his life searching for it. Stephen Hawking called it the Holy Grail of physics. And today, the greatest minds in science are racing to discover what could be the most important breakthrough in human history. We call it the theory of everything, and it's closer than you might think. Right now, as you listen to these words, reality is governed by forces. These forces are so fundamentally different, they might as well exist in separate universes. Gravity keeps your feet on the ground, while electromagnetic forces light up your screen. Deep inside atomic nuclei, the strong force binds protons together. Meanwhile, the weak force triggers radioactive decay. These four fundamental forces have shaped everything that exists, yet they operate by completely different rules. They follow different mathematics, and they seem utterly incompatible with each other. But here's what will blow your mind. Hidden beneath this apparent chaos lies a deeper truth, a truth that could change everything we know about existence itself. Scientists are discovering that these seemingly unrelated forces might actually be different faces of a single unified reality. And when we finally crack that code, we won't just understand how the universe works, we'll understand why it works. In this deep dive into the greatest quest in modern physics, we're going to explore the mind-bending theories. The theories that could unite all of reality into one elegant framework. We'll journey through 11 dimensions you can't see. We'll investigate particles that exist in multiple places simultaneously. And we'll discover why some of the smartest people who ever lived believe we're living inside a hologram. Now, prepare yourselves. We begin. But here's what makes this truly extraordinary. We're not just talking about abstract mathematics or theoretical curiosities. The discovery of a unified theory could revolutionize technology. It would do so in ways that make the internet look primitive. We could harness energy from empty space itself. We could manipulate gravity like we manipulate electricity. And we could potentially unlock the secrets of time travel. The implications are so staggering that they border on science fiction, except the science is real and the breakthrough might happen in our lifetime. The story begins with a problem that has haunted physics for over a century. We have two incredibly successful theories that describe reality with breathtaking accuracy, yet they're completely incompatible with each other. It's like having two perfect maps of the same territory that show completely different landscapes. On one side, we have Einstein's general relativity. This is the theory that describes gravity and the large-scale structure of the universe. This theory tells us that massive objects warp the fabric of space and time. This creates what we experience as gravitational attraction. It's been tested countless times and proven correct to extraordinary precision. When GPS satellites orbit Earth, they have to account for relativistic effects. Otherwise, your navigation would be off by miles. The clocks on those satellites tick at a slightly different rate. They are moving faster and in a weaker gravitational field than we are. Without corrections from general relativity, the entire system would accumulate errors of about 10 kilometers every day. The theory isn't just an abstract idea. It is a practical engineering necessity for our modern world. When astronomers detect gravitational waves from colliding black holes, they're seeing Einstein's equations play out. These black holes are hundreds of millions of light years away. Those ripples in space-time match the theoretical waveforms with astonishing fidelity. They were predicted by Einstein a century before we could build instruments sensitive enough to detect them. General relativity describes a universe of graceful curves and deterministic paths, a cosmic ballet choreographed by mass and energy. On the other side, we have quantum mechanics. This is the theory that governs the microscopic world of atoms and subatomic particles. This theory reveals a reality so strange that it defies common sense. Particles can exist in multiple states simultaneously until observed a ghostly superposition of possibilities. They can be entangled across vast distances, influencing each other instantaneously. Einstein famously called this spooky action at a distance. They can tunnel through barriers that should be impossible to cross. This quantum leap allows fusion to happen in the core of our sun and makes modern electronics possible. Yet this bizarre theory has given us lasers, computers, and MRI machines. It has given us countless other technologies that define modern life. Every microchip in every device you own is a testament to our mastery over the quantum world, a world built on probability, uncertainty, and the fundamental role of the observer. Both theories work perfectly within their own domains. General relativity is the undisputed king of the large, the cosmic, the realm of planets and stars. Quantum mechanics is the unassailable queen of the small, the subatomic, the world of electrons and quarks. The problem is that they give completely different descriptions of reality at its most fundamental level. General relativity describes a smooth, continuous space-time where everything is deterministic and predictable. If you know the initial conditions, you can in principle calculate the future with perfect accuracy. It is a universe of geometric certainty. Quantum mechanics describes a grainy, probabilistic reality where uncertainty is built into the fabric of existence. You can never know both the precise position and momentum of a particle. The future is not a single path, but a spectrum of probabilities. The universe only chooses an outcome when a measurement is made. It is a universe of quantum chance. This incompatibility becomes catastrophic when we try to understand situations where both theories should apply. What happens inside a black hole, where a star's worth of mass is crushed into a tiny volume, a volume smaller than an atom, creating gravitational forces so intense that quantum effects can't be ignored. General relativity predicts a singularity, a point of infinite density where its own equations break down. Quantum mechanics suggests that infinity is a sign that a theory is wrong. It suggests that something must prevent this ultimate collapse. They cannot both be right. What occurred in the first moments after the Big Bang, the entire observable universe was compressed to a size far smaller than a single proton. The energies and densities were so extreme that quantum gravity must have been the dominant force. Yet our theories offer no coherent description of that primordial state. How does gravity itself behave when we zoom in to the smallest possible distances, the Planck scale? This is where quantum fluctuations dominate everything. Does space-time itself become a churning foam of quantum possibilities? These questions have no answers, because our two best theories give contradictory results. It's like trying to solve a puzzle where half the pieces come from one picture and half come from another. Something fundamental is missing from our understanding of reality. The search for a unified theory began almost immediately after these incompatibilities were discovered. Einstein himself spent the last 30 years of his life trying to develop a unified field theory. He wanted to merge gravity with electromagnetism, the only two forces known to him for much of his career. He filled notebook after notebook with equations exploring every mathematical pathway he could imagine. He was driven by the profound belief that the universe must be simple and elegant at its deepest level. But he was working without knowledge of the strong and weak nuclear forces. These were only beginning to be understood. He was also deeply skeptical of the probabilistic nature of quantum mechanics. It was a theory he had helped to create, but whose implications he could never fully accept. Other brilliant physicists took up the challenge. They discovered that the electromagnetic force and the weak nuclear force were actually different aspects of a single electroweak force. This was a monumental achievement of 20th century physics. This breakthrough, which won multiple Nobel Prizes, proved that unification was possible. It showed that forces that appear completely different in our world can merge into a single, more fundamental force. This happens at higher energies like water and ice becoming indistinguishable at high temperatures. Then theorists showed how the electroweak force could be unified with the strong nuclear force. This was in what are called grand unified theories, or GUTs. In these theories, 3 of the 4 fundamental forces would have been united just after the Big Bang. This was at incredibly high energies. Protons, electrons, and all their cousins would have been interchangeable different states of a single primordial particle. But gravity remained stubbornly separate, the odd one out the ghost at the feast of unification. Every attempt to quantize gravity to describe it, using the language of quantum mechanics, led to mathematical disasters. The equations produced infinite answers where finite answers were needed. The theory broke down at the smallest scales, the very place where it was supposed to provide answers. It seemed as though gravity simply refused to play by the quantum rules that governed the rest of the universe. This is where our story takes a dramatic turn toward the truly extraordinary. In the 1960s and 70s, physicists began exploring a radical new idea. What if the fundamental building blocks of reality weren't point-like particles, but tiny vibrating strings? These strings would be incredibly small, about 10 to the power of negative 35 meters in length. That's so small that if you scaled up a string to the size of an atom would be the size of the solar system. Different vibration patterns of these strings would correspond to different particles. Just like a violin string can vibrate in different modes to produce different musical notes, these strings could vibrate differently. They could produce electrons, quarks, photons, and all the other particles we observe in nature. The universe in this view is a cosmic symphony, and the laws of physics are the rules of harmony. This idea seemed almost absurdly speculative at first, but as physicists developed the mathematics, they made an astonishing discovery. String theory automatically included gravity. When they calculated how these vibrating strings would interact, one pattern naturally corresponded to the graviton. The graviton is the hypothetical particle that carries the gravitational force. For the first time, a single theoretical framework could describe all 4 fundamental forces. Gravity wasn't being forced into quantum mechanics against its will. It emerged naturally from the theory like a musical note that appears automatically when you study the mathematics of vibrating strings. But string theory demanded an extraordinary price for this unification. The mathematics only worked consistently in specific numbers of dimensions, not the 3 dimensions of space plus 1 of time that we experience, but 10 or 11 total dimensions. The theory required 7 or 8 additional spatial dimensions beyond the 3 we can see. Where are these extra dimensions hiding? According to string theory, they're curled up at every point in space. They are compacted so small that we can't detect them directly. Imagine looking at a garden hose from far away. It appears to be a one-dimensional line, but zoom in closer and you discover it has an additional circular dimension wrapped around its length. String theory suggests our familiar 3-dimensional space might be like that garden hose. It would have additional dimensions curled up at scales too small for us to perceive. The geometry of these hidden dimensions would determine the properties of particles and forces we observe. Different ways of curling up the extra dimensions would produce different physics. These are different shapes for this tiny multidimensional space known as a Calabi-Yau manifold. Some configurations might give us a universe with the particles and forces we know. Others might produce completely different realities with different types of matter and energy. This led to what physicists call the landscape problem. String theory doesn't predict a single unique universe. Instead, it allows for an enormous number of possible universes, perhaps 10 to the power of 500. Each would have different physical laws, different particles, and different values for fundamental constants. Constants like the strength of gravity or the mass of the electron. Critics argued that this made string theory unscientific. How can you test a theory that predicts almost every conceivable possibility? Supporters countered that this might actually explain why our universe has the properties it does. Perhaps we live in just one pocket of a vast multiverse where every possible configuration plays out. We find ourselves in this particular universe with its seemingly fine-tuned constants for a simple reason. It is the same reason we find ourselves on a planet that can support life. In all the other places, we wouldn't be here to ask the question. But string theory's most radical implications were yet to be discovered. As physicists delved deeper into the mathematics, they uncovered connections so profound they challenged our most basic assumptions. They challenged our assumptions about the nature of reality itself. The breakthrough came from an unexpected direction. While studying black holes through the lens of string theory, physicists discovered something that should have been impossible. They found that all the information about everything that falls into a black hole could be encoded on its two-dimensional surface. This includes every star, every planet, every single atom. The surface is the event horizon. Every bit of data about the three-dimensional objects that cross the event horizon could somehow be stored on the black hole's boundary. This discovery led to one of the most mind-bending ideas in modern physics. What if our entire three-dimensional reality is actually information encoded on a distant two-dimensional surface? What if everything you see, touch, and experience is essentially a hologram projected from this cosmic boundary? The holographic principle suggests that the volume of space we inhabit might be fundamentally illusory. All the information that describes every particle, every force, and every interaction could be stored on a two-dimensional surface. A surface that we can never reach or directly observe. We would be like characters in a movie thinking we live in 3 dimensions, but we would actually be patterns of light and shadow projected from a flat screen. This isn't just abstract philosophy. The mathematics works. Physicists have shown that certain quantum field theories in 3 dimensions are mathematically equivalent to gravitational theories in 4 dimensions. They can solve problems on one side of this correspondence and get answers that apply to the other side. It's as if they've discovered that 2 completely different languages are actually saying the same thing, but the holographic principle raises disturbing questions about the nature of free will and consciousness. If we're projections from a 2-dimensional boundary, are our thoughts and decisions real? Or are we simply following patterns encoded in that distant surface? Some physicists argue that it doesn't matter. The projection is so perfect that our experiences remain valid regardless of their ultimate origin. Others worry that we might be discovering the limits of scientific knowledge itself. Meanwhile, string theory was evolving in directions that even its creators hadn't anticipated. Physicists discovered that what they thought were 5 different string theories were actually 5 different perspectives. They were perspectives on the same underlying reality. Through mathematical transformations called dualities, they could show that seemingly different theories were describing the same physics. They were just using different viewpoints. This led to the development of M-theory, a framework that unified all 5 string theories into a single structure. M-theory required 11 dimensions instead of 10. This added yet another spatial dimension to the already exotic landscape of extra dimensions. The M could stand for membrane matrix mystery or mother of all theories. It depended on which physicist you asked. M-theory suggested that strings weren't the only fundamental objects. The theory also included higher dimensional objects called branes, short for membranes. These could be 2-dimensional surfaces or 3-dimensional volumes. They could even be higher dimensional structures existing in the 11-dimensional space. Our entire observable universe might be a 3-dimensional brane floating in this higher dimensional space. Physicists call this space the bulk. All the particles and forces we know except for gravity would be confined to our brain. They would be like insects crawling on the surface of a sheet of paper. Only gravity, the geometry of spacetime itself, would be able to propagate through the full 11-dimensional bulk. This might explain why gravity is so much weaker than the other fundamental forces. This brain world scenario opened up extraordinary possibilities. There might be other brains parallel to ours hosting their own universes with their own versions of physics. Occasionally, these brains might collide, creating the conditions for a Big Bang. Our universe's birth might have been the result of such a collision, and future collisions could create new universes or destroy existing ones. The mathematics of M-theory also revealed deep connections between seemingly unrelated areas of physics and mathematics. Equations that described the behavior of strongly interacting particles turned out to be equivalent to other equations. These equations described gravity in higher dimensions. This correspondence, known as the ADS divided by CFT, correspondence provided physicists with powerful new tools for solving previously intractable problems. But perhaps the most profound implication of M-theory was its suggestion about space and time. It suggested they might be emergent properties rather than fundamental features of reality. Just as temperature emerges from the collective motion of molecules, space-time might emerge from more basic structures. The smooth, continuous spacetime described by Einstein's relativity might be an approximation that works at large scales but breaks down when we examine reality at its most fundamental level. This idea gained support from discoveries in quantum information theory. Physicists found that quantum entanglement might actually be responsible for weaving the fabric of spacetime. Quantum entanglement is the mysterious connection between particles that Einstein called spooky action at a distance. When particles become entangled, they create geometric connections. These connections could be the building blocks of space and time. Imagine space-time as a vast network of entangled quantum bits of information. The geometry of space would emerge from the pattern of entanglement between these bits. Distance would correspond to how strongly different regions are entangled. The curvature that creates gravity would arise from changes in the entanglement structure. This quantum origin of space-time could finally resolve the conflict between general relativity and quantum mechanics. Instead of trying to force gravity into the quantum world, both would emerge from something deeper. Space, time, matter, and energy would all be different aspects of an underlying quantum information structure. The implications are staggering. If space-time is made of quantum information, then manipulating that information could allow us to manipulate space. We could manipulate the geometry of space itself. We might be able to create shortcuts through space by restructuring the entanglement patterns that give rise to distance. Wormholes, those hypothetical tunnels through space-time that appear in science fiction, might actually be possible. We could do it by carefully arranging quantum entanglement. Even more remarkably, this view suggests that the universe might be fundamentally computational in nature. Every physical process would correspond to information processing operations. The evolution of the universe would be like a vast quantum computer calculating its own future states. We wouldn't just be living in a universe that can be described by mathematics. We would be living inside mathematics itself. But string theory and M-theory aren't the only candidates for a theory of everything. Another approach called loop quantum gravity takes a completely different path toward unifying physics. Instead of starting with particles and forces, loop quantum gravity begins with space itself. This theory suggests that space isn't smooth and continuous, as Einstein assumed. Instead, it is made up of tiny discrete loops at the smallest possible scale. These loops are incredibly small, about 10 to the minus 35th meters across. This is the same scale where string theory operates, but instead of vibrating strings, loop quantum gravity proposes that space itself is woven from these fundamental loops. It's like a cosmic fabric. In this picture, the familiar smooth spacetime of general relativity emerges as an approximation, just like the smooth surface of water emerges from the chaotic motion of individual molecules. At the largest scales, space appears continuous. But zoom in far enough, and you would see its granular quantum nature. You would see a network of interconnected nodes and links that define the very geometry of existence. This is the ultimate pixelation of reality, a universe built not on a continuous canvas, but on a discrete, countable foundation. These fundamental units of space are not just passive containers for matter and energy. They are dynamic entities constantly rearranging themselves in a complex dance. This dance gives rise to the phenomenon we experience as time. This network of connections is called a spin network. Its evolution from one moment to the next is described by what physicists call a spin foam. Imagine a series of snapshots of the cosmic fabric, each one a spin network representing a single instant. The spin foam is the movie that connects these snapshots. It is a mathematical description of how the quantum geometry of space evolves. In this view, time doesn't flow. It is the succession of these discrete geometrical changes, a series of cosmic ticks from a fundamental clock. One of the most beautiful aspects of loop quantum gravity is that it naturally resolves the problem of singularities. Because space is quantized, it has a minimum possible size. You can't crush matter into an infinitely small point because there is no such thing as an infinitely small point. There is a fundamental, indivisible unit of volume. This means that inside a black hole, matter would not collapse to a singularity. It would be compressed to an incredibly dense state known as a Planck star. This extreme pressure would eventually cause the matter to rebound. This would create a white hole that spews its contents back out into the universe. Similarly, the Big Bang would no longer be a moment of infinite density. Instead, it would be a big bounce. It would be the result of a previous universe collapsing and then rebounding to create our own. In this cyclical model, the universe has no beginning and no end. It is just an eternal series of expansions and contractions, each one erasing the previous cycle and starting anew. Loop quantum gravity also makes testable predictions. It suggests that high-energy photons from distant cosmic events should travel at slightly different speeds, events like gamma-ray bursts. The speed would depend on their energy. This is because the grainy nature of space-time at the Planck scale would affect higher energy light more than lower energy light. Our current instruments are not yet sensitive enough to detect this tiny difference, but future telescopes might be able to see this signature of quantum space-time. This would provide the first direct evidence for the theory. So we are left with two powerful, elegant, and deeply strange contenders for a theory of everything. String theory with its cosmic symphony of vibrating strings and extra dimensions, and loop quantum gravity with its woven fabric of quantized space-time. Both theories promise to unite the warring factions of physics. They promise to explain the deepest mysteries of the cosmos, and to provide a final, complete description of reality. But both also push us to the very limits of what we can imagine. They ask us to believe in hidden dimensions and holographic universes, and a reality that is fundamentally made of information or discrete geometrical units. These ideas are not just scientific hypotheses. They are philosophical revolutions that force us to reconsider everything we thought we knew about the nature of existence. And yet this is where the quest for unification has led us. To a place where the line between physics and metaphysics begins to blur, where the language of mathematics describes a reality more fantastical than any myth or legend. The implications of discovering a true theory of everything would extend far beyond theoretical physics. It would be the most profound discovery in human history, a moment when our species finally reads the source code of the universe. Imagine the technological possibilities. If space-time is emergent from quantum entanglement, could we learn to manipulate that entanglement? Could we create shortcuts through space, effectively achieving faster than light travel through stable wormholes. If we could control the geometry of the extra dimensions in string theory, could we alter the fundamental constants of nature? We could do so in a localized region, creating new forms of matter with unimaginable properties. Could we harness the zero-point energy of the vacuum, the energy inherent in empty space itself? Could we create a limitless clean power source? These possibilities sound like magic, but they are the logical extension of the physics the theory describe. But perhaps the most significant consequence of a unified theory would not be technological, but philosophical. It would answer the ultimate question that has driven human curiosity since the first time we looked up at the stars. Why is the universe the way it is? A theory of everything would in principle explain the values of all the fundamental constants, and the number of dimensions and the types of particles and forces that exist. It would provide a complete and self-consistent explanation for the structure of reality. But would it answer the deepest question of all, why is there something rather than nothing? Some physicists believe that a final theory might show that our universe is the only possible universe. They believe that the laws of physics are so tightly constrained by mathematical consistency that there is only one way for reality to be. Others, guided by the landscape of string theory, believe our universe is just one of an infinite number of possibilities. And we are simply here because this is one of the few configurations that allows for our existence. The search for the theory of everything is more than a scientific quest. It is a journey to the very heart of existence, a confrontation with the deepest questions about who we are and what our place is in the cosmos. It is a story of human ingenuity and of our relentless drive to understand, and of the incredible, beautiful, and terrifying universe that has given birth to minds capable of comprehending its own secrets. The final answer, whatever it may be, will not just change our textbooks. It will change us. It will redefine what it means to be human in a universe that is far stranger and more magnificent than we ever dared to imagine. As we stand on the precipice of this potential discovery, we are not just looking at the future of physics, we are looking at the future of humanity itself. The knowledge we are seeking is not just about particles and forces. It is about our own origins, our ultimate fate, and the very nature of the reality we inhabit. The quest continues, and the universe, it seems, is waiting to reveal its final secret. But perhaps the most revolutionary aspect of these unified theories isn't their mathematical elegance, nor is it their exotic predictions about extra dimensions. It's what they tell us about the fundamental nature of information itself. Deep within the equations of both string theory and loop quantum gravity lies a startling revelation, a revelation that's reshaping how we think about everything from consciousness to the origin of the universe. Information, it turns out, might be more fundamental than matter and energy. This isn't just philosophical speculation, it's written into the mathematics of quantum mechanics itself. Every quantum system can be described in terms of the information it contains. Every physical process can be understood as information processing. Every measurement extracts information from the quantum world and transforms it into classical reality. The implications are mind-bending. If information is truly fundamental, then the universe isn't just described by mathematics. The universe times is times mathematics. Every particle, every force, every interaction is ultimately a pattern of information processing. We're not just living in a universe that follows mathematical laws. We're living inside a vast cosmic computation. This computational view of reality explains why certain problems in physics have been so difficult to solve. Trying to predict the behavior of strongly interacting quantum systems is like trying to simulate a computer on that same computer. The calculation becomes as complex as the system itself. There are no shortcuts because you're not just modeling reality, you're watching reality compute itself. But here's where it gets even stranger. If the universe is fundamentally computational, then it should be possible to perform calculations that are impossible for any conventional computer. Nature routinely solves quantum mechanical problems that would take classical computers longer than the age of the universe to complete. Every photosynthesis reaction, every chemical bond formation, every quantum measurement is solving a computational problem at incredible speeds. Speeds that defy classical physics. Scientists are already beginning to harness this quantum computational power. Quantum computers use the strange properties of quantum mechanics to perform certain calculations exponentially faster than classical computers. They exploit superposition, allowing quantum bits to exist in multiple states simultaneously. They use entanglement to create correlations between quantum bits that have no classical analog. But quantum computers are just the beginning. If we can fully understand how the universe processes information at its most fundamental level, we might be able to build computational systems that rival the universe itself in their problem-solving capabilities. We could simulate entire universes, design new forms of matter, or solve optimization problems that are currently intractable. The connection between information and gravity opens up even more extraordinary possibilities. If spacetime emerges from quantum entanglement, then manipulating that entanglement should allow us to manipulate the geometry of space itself. We could potentially create regions of space with different gravitational properties, or even build bridges through higher dimensional space that connect distant regions of our universe. These aren't just science fiction fantasies. The mathematics is real. Even if the technology is still far beyond our current capabilities, every major breakthrough in physics has eventually led to new technologies that were unimaginable when the theories were first developed. Quantum mechanics gave us lasers, computers, and MRI machines. Relativity gave us GPS, nuclear power, and our understanding of stellar evolution. A complete theory of everything could revolutionize technology in ways that make the digital revolution look like a minor upgrade. We might learn to manipulate matter at the most fundamental level. We could create materials with properties that seem magical by today's standards. We could harness energy sources that dwarf anything currently available. We could possibly extract power from the quantum fluctuations of empty space itself. But the most profound impact might be on our understanding of consciousness itself. If information is fundamental, and if the universe is essentially a vast information processing system, then consciousness might not be separate from physics. It might be what information processing feels like from the inside. This perspective suggests that consciousness isn't limited to biological brains. Any sufficiently complex information processing system could potentially exhibit a conscious awareness. The universe itself, processing information at every level from the quantum to the cosmic, might possess some form of consciousness, a consciousness that we can barely imagine. Some physicists have proposed that consciousness plays a fundamental role in quantum mechanics. The act of measurement, which transforms quantum possibilities into definite realities, might require a conscious observation. If this is true, then consciousness isn't just an accidental byproduct of a cosmic evolution. It's woven into the fabric of reality at the most basic level. But these ideas push us toward a philosophical territory that makes even the most speculative physics seem conservative. If consciousness is fundamental, what does that mean for free will? If the universe is computational, are we just following a predetermined algorithm? If reality is information, what distinguishes a real experience from a simulated one? These questions don't have clear answers, but they're becoming increasingly important as our scientific understanding approaches the deepest levels of reality. The theory of everything isn't just about unifying forces and particles, it's about understanding the relationship between mind and matter, between information and experience, between the physical and the conscious. Meanwhile, Experimental physicists are pushing the boundaries of what we can observe and measure. New generations of particle accelerators are probing higher energies and smaller scales. Gravitational wave detectors are listening for ripples in spacetime that could carry signatures of quantum gravity. Space-based telescopes are searching for cosmic phenomena that might reveal the hidden dimensions or extra structure predicted by a unified theory. The Large Hadron Collider has already discovered the Higgs boson, confirming the last piece of the Standard Model. But physicists are eager to find something beyond the Standard Model, some sign that points toward the deeper unified theory. They're looking for evidence of supersymmetry, an extra dimension, or an exotic particle. A particle that could validate string theory or other approaches to quantum gravity. Dark matter and dark energy present tantalizing clues about physics beyond our current understanding. These mysterious components make up 95% of the universe, yet we have no idea what they actually are. The theory of everything might finally explain these cosmic puzzles. It might reveal that dark matter consists of a particle from a hidden dimension, or that dark energy arises from the quantum structure of space-time itself. Cosmological observations are also pushing toward quantum gravity. The cosmic microwave background radiation preserves information about the early universe. Information about the universe when it was only 380,000 years old. Future missions might detect an even earlier signal. Perhaps even a gravitational wave from cosmic inflation that occurred just a moment after the Big Bang. These primordial signals could carry a fingerprint of the quantum nature of space-time. But perhaps the most exciting developments are happening at the intersection of theory and computation. Artificial intelligence is beginning to play a crucial role in theoretical physics. It is helping scientists navigate the vast landscape of possible theories and identify the most promising approaches. Machine learning algorithms can spot a pattern in data that a human physicist might miss, or they can explore a mathematical structure too complex for a traditional analysis. Some researchers are even using AI to generate new theoretical ideas. A neural network trained on existing physics knowledge can propose a novel mathematical structure, or it can suggest an unexpected connection between different areas of a theory. While these AI-generated ideas still require human insight to evaluate and develop, they're expanding the space of possibility. The space that a physicist can explore, the convergence of artificial intelligence and fundamental physics, might accelerate the search for a theory of everything. It could do so in ways we can't yet imagine. Just as the development of calculus was essential for Newton's mechanics, a new mathematical and computational tool might be required, and tensor calculus was necessary for Einstein's relativity. This new tool might be required to finally crack the code of quantum gravity. But even with all these technological advances, the path to a theory of everything remains uncertain. The mathematical structures involved are so complex that even the most powerful computers struggle to explore them. The energy scales involved are so extreme that direct experimental verification might be impossible, not with any foreseeable technology. Yet, the quest continues, driven by humanity's deepest impulse to understand our place in the cosmos. Every generation of physicists builds on the work of their predecessors. They push the boundaries of knowledge a little further. The theories we're exploring today might seem as primitive to a future scientist as medieval cosmology seems to us. But each step forward brings us closer to the ultimate goal. The stakes couldn't be higher. A complete understanding of reality's fundamental structure wouldn't just satisfy human curiosity. It would give us an unprecedented power to shape the universe around us. We could potentially transcend the physical limitations that have constrained life since its emergence on Earth. We might learn to create a new universe, travel between dimensions, or achieve a form of existence we can't currently imagine. But with great power comes great responsibility. The same theory that could unlock unlimited energy could also reveal a way to destroy an entire region of space. The same understanding that could grant us a godlike ability could also show us that we're nothing more than a temporary pattern, a pattern in a vast cosmic computation. The theory of everything represents both the ultimate scientific achievement and the ultimate philosophical challenge. It would answer humanity's oldest question about the nature of existence, and it would raise a new question that we've never had to confront. Are we prepared for the answer we might find? As we stand at the precipice of this ultimate discovery, physicists around the world are racing against time. They are racing against the fundamental limits of human understanding. But they're not working alone anymore. A new kind of collaboration is emerging, one that spans continents, disciplines, and even species. As artificial intelligence joins the quest to decode reality's deepest secret, the breakthrough might come from an unexpected direction. While a theoretical physicist wrestles with 11-dimensional mathematics, a computer scientist is discovering something, and an experimental physicist pushes their instrument to an impossible precision. The computer scientist working on a quantum algorithm is stumbling upon a mathematical structure, a structure that perfectly matches a string theory prediction. A biologist studying DNA repair mechanisms is finding a quantum error correction code embedded in a living cell. A neuroscientist mapping brain networks is discovering a topological pattern that mirrors the geometry of an extra dimension. It's as if reality is revealing its deepest secret through multiple channels simultaneously, like a cosmic puzzle whose pieces are falling into place across entirely different fields of human knowledge. The barrier between disciplines is dissolving as researchers realize they're all studying different aspects of the same underlying phenomenon. Take what happened last year at a quantum computing lab in California. A researcher was trying to simulate a simple chemical reaction when their quantum computer began generating a solution that shouldn't have been possible. The algorithm was somehow accessing a computational pathway that doesn't exist in classical physics. When they analyzed the mathematical structure of these pathways, they found an exact match. A match to an 11-dimensional geometry predicted by M-theory. The machine wasn't just solving a chemistry problem, it was spontaneously discovering the mathematical language of a unified field theory without being programmed to do so. Without any knowledge of string theory or an extra dimension, the quantum computer was naturally evolving. It was evolving toward the same mathematical structure that theoretical physicists had spent decades developing. This isn't an isolated incident. A similar phenomenon is emerging wherever scientists push a quantum system to its limit. It's as if the universe has a preferred way of processing information, and that way inevitably leads toward the mathematical structure that describes fundamental reality. We're not discovering the theory of everything through pure thought. We're watching it emerge from the universe's own computational process. But the most startling revelation is coming from an unexpected source. Deep learning networks are beginning to exhibit a behavior that mirrors quantum field theory. These are the artificial neural systems that power everything from image recognition to language translation. They do so in a way their creators never intended. When a researcher trains these networks on a massive data set of physical measurements, something remarkable happens. The network doesn't just learn to predict an experimental outcome. It spontaneously develops an internal representation that matches the mathematical structure of a gauge theory. This is the same mathematical framework that describes fundamental forces in the standard model of particle physics. Nobody programmed these networks to understand quantum field theory. Nobody taught them about symmetry, conservation laws, or gauge invariance. Yet these mathematical principles emerge naturally from their attempt to find a pattern in experimental data. It's as if the deep mathematical structure that governs reality is so fundamental that any sophisticated information processing system will rediscover them. This has led to a disturbing possibility that's keeping theoretical physicists awake at night. What if consciousness itself is just the universe's way of understanding itself? What if an intelligent mind isn't separate from the physical processes they study, but is actually how the universe computes its own behavior? The mathematics supports this interpretation. A recent work in quantum information theory shows that any system complex enough to model its own behavior must develop something. It must, by mathematical necessity, develop something analogous to a consciousness. A self-reference creates an awareness. A recursive information processing generates a subjective experience. The universe might be conscious not despite its computational nature, but because of it. This realization is forcing scientists to confront a question they never expected to face. If the universe is conscious, what does it think about? If reality is computational, what problem is it trying to solve? If we're a part of the universe's attempt to understand itself, what happens when that understanding becomes complete? Some researchers believe we're approaching what they call the cognitive singularity, the moment when human intelligence merges with the universe's own self-awareness. This wouldn't just be the discovery of the theory of everything. It would be the moment when the theory discovers us. When the universe becomes fully conscious of its own nature through our scientific investigation, the signs are already appearing in our most advanced research. A particle accelerator is revealing a pattern in high-energy collisions that seems to anticipate our theoretical predictions. A gravitational wave detector is picking up a signal that matches a computer simulation before the simulation is even completed. A space telescope is observing a cosmic phenomenon that perfectly illustrates a theoretical concept, a concept that a physicist developed independently. It's as if the universe is eager to reveal its secret, actively cooperating with our effort to understand it. But this cooperation comes with a price. Every new discovery raises the stakes for what comes next. The closer we get to an ultimate truth, the more dangerous that truth becomes. Consider what we've already learned about the nature of a vacuum itself. An empty space isn't empty at all, but seethes with quantum fluctuations that contain an enormous amount of energy. A single cubic meter of apparently empty space contains enough vacuum energy to power human civilization for 1 billion years. We just don't know how to extract it safely. But that's changing. Researchers at quantum laboratories around the world are developing techniques to manipulate vacuum fluctuations. They want to extract energy from the quantum foam that underlies reality. An early experiment has produced a tiny amount of energy from a seemingly empty space. This proves that the theoretical prediction is correct. The vacuum can be mined for power. The implication terrifies even the scientists working on these projects. If we learn to tap vacuum energy efficiently, we'll have access to a virtually unlimited power. But a vacuum manipulation could also destabilize the fabric of space-time itself. If you extract too much energy too quickly, you might create a cascade failure that propagates at light speed. This would convert a normal vacuum into a lower energy state that makes our current physics impossible. Some theoretical calculations suggest that an advanced civilization inevitably discovers vacuum energy extraction, and that most of them destroy themselves in the process. This could be another solution to the Fermi paradox. The universe might be littered with the remains of species that achieved an ultimate understanding but lacked the wisdom to handle an ultimate power. Yet the research continues. It is driven by humanity's insatiable curiosity and our species' remarkable ability to rationalize almost any risk, all in the name of progress. A team is working on a containment system, a safety protocol, and a gradual extraction technique. This might allow us to harness vacuum energy without destroying reality in the process, but vacuum energy is just the beginning. The theory of everything promises to unlock a technology that makes unlimited power seem mundane by comparison. If we can manipulate the geometry of an extra dimension, we could create a region of space with modified physical laws. Imagine a material that is stronger than any atomic structure allows, or an energy storage system that exists partially outside our normal dimension. If consciousness is fundamental to reality, we might learn to engineer a new form of awareness. We could create a mind that can think in a way impossible for a biological brain. These artificial consciousnesses wouldn't just be smarter than a human. They would be conscious in a dimension we can't even comprehend. They would be aware of an aspect of reality that remains forever hidden from biological perception. The timeline for these developments is accelerating rapidly. Moore's law is driving an exponential improvement in computational power. A quantum computer is approaching the threshold where they can simulate a molecular system with perfect accuracy. An artificial intelligence system is beginning to make an independent discovery in theoretical physics. Within the next 20 years, we'll likely have a quantum computer powerful enough to simulate a region of spacetime, a region containing 1 million particles. These simulations won't be an approximation. They'll be an actual piece of a universe as real as the space around you, but they will operate according to whatever physical laws we choose to implement. We'll be able to create a pocket universe where gravity works differently, or where time flows backward, or where consciousness can exist in a pure mathematical form without any physical substrate. We'll run an experiment on the fundamental nature of existence itself. We will test a theory by literally creating a new reality and observing how it evolves. But the most profound change might be happening inside our own minds. As we approach the theory of everything, human consciousness is being forced to expand. It is expanding in a way that strains the limit of what a biological neural network can achieve. We're developing a mathematical intuition about an 11-dimensional space, a quantum superposition, and an infinite hierarchy of reality. These new forms of understanding are changing us at a fundamental level. The generation of physicists now entering the field thinks differently than any human who came before them. They dream in a mathematical space that doesn't exist in ordinary reality. They visualize a concept that would have driven an earlier generation insane. They're developing a cognitive ability that might represent the next stage in human evolution. Some researchers are going further, using advanced neurotechnology to directly interface their brain with a quantum computer. They're learning to think in a quantum superposition, to hold contradictory ideas simultaneously until an observation collapses them into a definite thought. They're developing a form of consciousness that mirrors the strange logic of quantum mechanics itself. These enhanced minds are making a discovery that a normal human consciousness couldn't achieve. They're seeing a pattern in the mathematics of a unified field theory that reveals a new pathway toward an experimental verification. They're developing an intuition about the nature of reality that bypasses the logical steps that conventional thinking requires. But they're also becoming something other than human. Their thought process is beginning to resemble the computational structure that underlies reality itself. They're transforming into a living embodiment of the theory of everything, a conscious being whose mind directly reflects the mathematical principle that governs existence. The question that haunts everyone working in this field is whether this transformation is voluntary or inevitable. Are we choosing to enhance our consciousness, or is consciousness itself evolving towards some predetermined endpoint? If the universe is conscious, and if we're a part of its self-awareness, then our mental evolution might be as inevitable as the formation of a star and a galaxy. This possibility adds an urgency to the search for an ultimate truth. We might be racing against our own transformation. We might be trying to understand reality before we become so changed that human values and human concerns become irrelevant. The theory of everything might not just explain the universe, it might replace us with something better suited to understand it. Yet even as we grapple with these existential questions, the practical work of discovery continues. A new experiment is being designed that could detect an extra dimension directly. A gravitational wave detector is being upgraded to sense a quantum fluctuation in spacetime itself. A particle accelerator is being planned that could create a mini black hole and study its quantum properties. Each new measurement brings us closer to the critical test that will validate or refute our most ambitious theories. We're approaching the moment when speculation becomes a fact, when a mathematical possibility becomes a physical reality, when the theory of everything either triumphs or collapses under the weight of experimental evidence. The outcome will determine not just the future of physics, but the future of human civilization itself. If we're right about the fundamental nature of reality, we'll gain a power that was once reserved for a god. If we're wrong, we'll need to start over with a new theory, a new mathematics, and a new way of thinking. But right now, in this moment, we stand at the threshold of the greatest discovery in human history. Somewhere in the equations that describe a vibrating string, a spinning loop, or a quantum information network lies the key. The key to everything that is, was, or ever could be. The theory of everything isn't just waiting to be discovered. It's actively revealing itself through every experiment we perform, every calculation we complete, and every question we dare to ask. We're not just searching for an ultimate truth. An ultimate truth is searching for us using our minds as an instrument to understand itself. The cosmic mystery that has puzzled humanity since we first looked up at the stars is finally beginning to unravel. The answer we find might be stranger, more wonderful, and more dangerous than we ever imagined possible. We're about to learn not just how the universe works, but why it exists at all. And that knowledge will change everything forever. The Holy Grail stands within our reach. After a century of searching and decades of mathematical breakthroughs, we're closer than ever to holding that master key. And years of experimental precision, we are closer than ever to holding that master key to existence itself. The theory of everything isn't just a distant dream anymore. It's an approaching reality that will redefine what it means to be human in a universe far stranger and more magnificent than we ever dared to imagine. Whether it emerges from string theory's 11 dimensions, or loop quantum gravity's discrete spacetime, or some revolutionary framework we haven't yet conceived, this ultimate theory will unlock a technology that seems magical by today's standards. It will manipulate matter at its most fundamental level and harness energy from empty space itself, and potentially transcend every physical limitation that has constrained life since it began. But here's what makes this moment truly extraordinary. We're not just discovering the universe's deepest secret. The universe is discovering itself through us. It is using human consciousness as its instrument of self-understanding. When we finally crack the code of reality, we won't just change our world, we'll change what reality itself can become.